Sarah Gladman from Glasgow Science Festival. Welcome to the final video from Get Me Into Orbit. We've had some fantastic questions from lots of schools that our resident space scientists and engineers have really enjoyed answering. So, without further ado, here are the answers.
So my name is Matteo Ceriotti. I'm Italian, originally from Italy. I'm British as well. I'm a lecturer in space systems engineering. This is my title. And what I do is I teach in space systems here at the University of Glasgow, and at the same time I do some research on orbits. I basically design where spacecraft and satellites fly. I design their orbits, I optimize their orbits to find the best trajectories they can actually follow. So it depends pretty much on the type of satellite. There are some very small satellites that orbit around the Earth, very close to the Earth, and their lifespan can be as short as a few days or a few weeks, and after that they simply burn into the atmosphere. And essentially these satellites are designed to perform very quick experiments, and sometimes they don't even have power sources that are renewable. They just use a battery, and once the battery is depleted, the satellite dies. However, there are some other satellites that have a much longer lifespan. For example, if we think about the Hubble Space Telescope, Hubble was launched into orbit in 1990 and is still operational today. So this is 28 years of operation and still fully functional. So that's pretty long lifetime. Something that I'd like to add is that today satellites that are orbiting around the Earth should be designed such that they actually re-enter and burn into the atmosphere within 25 years. And this is a policy that is enforced because we want to prevent the build-up of space debris in the future. Okay, first of all, I should say that it's extremely rare that satellites actually crash into the Earth. And the reason is because once the satellite goes very low, say at around 300-200 kilometers of altitude from the Earth, the atmosphere becomes very thick, and the satellite speed is so high that it causes friction between the satellite and the atmosphere, the air in the atmosphere, and the satellite burns, literally burns in the atmosphere itself. And therefore most of the satellites actually never collide back with the Earth, they simply burn into the atmosphere. However, there were cases in the past in which not entire satellites but parts of satellites actually got back into the surface of the Earth. This unfortunately has happened. We need to consider that the probability that that parts of satellite can hurt actual human beings on Earth is extremely small. It's calculated to be 1/1 trillion. So this is an extremely small probability, and in fact it's more likely that you're going to be hit by a lightning rather than as a part of a satellite. And something that was in the news lately is China's space station Tiangong-1. This was a space station that was launched in 2011, so 7 years ago, and is now non-functional, unfortunately, and completely out of control. And people are estimating that this space station or parts of it may actually fall onto the Earth by the end of March. So we are waiting to have more precise measurements to try to estimate where these parts may fall down. And if they fall down in the ocean, then this is clearly not a concern. And if we estimate that they may fall down in habitated areas, then of course some measurements can be taken. Yes, so small satellites are launched into space using rockets. However, launchers are designed to work with a certain amount of mass that they can carry. So if a launcher is designed for 1,000 kilograms of mass, it needs to be loaded with 1,000 kilograms. However, if in that mission is carrying a satellite that doesn't weigh 1000 kilograms, so it weighs maybe 950 kilograms, then there are 50 kilograms of mass left over for spare that need to be filled up with something. So rather than filling it up with dump mass, we'd rather fill it up with other smaller spacecraft. So it may be that there are 50 spacecraft, small spacecraft of 1 kilo that are waiting to be launched, and then they can be carried by this launcher, and this is called a piggyback launch. Another way of launching very small spacecraft is actually from the space station. So they're carried up to the space station using resupply vehicles, and the astronauts then release those microsatellites from the space station itself. Okay, the space station is designed for a crew of 6 astronauts at the same time. They can stay from a few weeks to a few months on the space station, and the crew is periodically replaced. However, not all the crew is replaced at the same time, but most of the missions replace only 3 members of the crew, such that there is always an overlap and there is always someone on the space station itself. Not very long. Rocket launchers are extremely fast and they accelerate very fast. It takes from 8 to about 20 minutes depending on the launcher and depending on the type of orbit. The reason is that space is not that far. Space is only 100 kilometers up, so it's not that far in terms of distance. And because rockets accelerate incredibly fast at 8, sometimes 10 times the force of gravity, it takes not a long time to get up 100 kilometers. I think that the very first idea of an artificial satellite came from Isaac Newton. Isaac Newton was a British scientist, is the same scientist who effectively explained for the first time how the gravity force works. Newton wrote this idea in one of his books in 1687, and Newton was 45 when he wrote this book. Newton came up with a thought experiment, so an experiment that he was actually thinking, he didn't really do, but he was thinking about this experiment. And the experiment is called the Newton cannonball. So he was imagining to climb up a very, very tall mountain, so tall that it could be outside of the atmosphere of the Earth. And then to have at the top of this mountain a very powerful cannon that could shoot a cannonball at an extremely high velocity. And with this experiment, he predicted that if the velocity is high enough and the mountain is high enough, then the cannonball would actually go around the orbit of the Earth and come back to the very same point at the top of the mountain, hitting effectively the cannon from the back. So effectively the cannonball would be in orbit around the Earth. So this is the very first time that someone is actually thinking of sending something artificially in orbit around our planet. The Russian scientist Konstantin Tsiolkovsky in the 1900s was the one, he's considered to be the father of rocketry, the father of astronautics, and he was the first one to write down mathematical laws for how rockets work and how spacecraft would work. However, the very first artificial satellite was launched by the Soviet Union in 1957. This was Sputnik 1. And it was a very simple satellite. It was just effectively a sphere with an antenna connected to it to transmit a radio signal back to Earth. Okay, first of all, we should say that it's very difficult to build and repair satellites in space, and mainly because there are very few people who can do it. There are only a few astronauts at most available to do it. However, it can be done. We are able to do it, and one of the prime examples of building something in space is in the International Space Station. Now, the space station is not actually built into space. Its components are built on Earth. However, they are assembled in space. So if you think about the first module of the space station, this was Zarya. It was launched in 1998, and it weighed 19 tons on Earth, and it was 12 meters long. So a relatively big module, but nowhere as big as what the space station is today. 159 components were added since then using a robotic arm assembled together, and now the space station is 419 tons and is 72 meters long, so much bigger than what it was before. We hope in the near future to be able to actually manufacture satellites in space autonomously using things like 3D printing that, for example, can extract resources either from a planet or even from an asteroid. Repairing satellites in space is also difficult, but again, it can be done. We can think, for example, of the Hubble Space Telescope. This was launched in 1990, and it was soon discovered that the main mirror of the telescope was actually damaged after launch, and therefore the telescope was basically unusable. And that's why we planned another space mission with the space shuttle in 1993, so 3 years later, in order to replace the main mirror. The mission was very successful. We managed to replace it, and now Hubble is working and is fully functional after 28 years. And it was actually serviced a number of additional times. So some of the other modules were replaced since then. So it is possible to service some satellites in space, especially when they're closer to the Earth. Of course, it's impossible to do so at the moment for satellites that are, for example, orbiting around Mars or farther planets, simply because it's impossible to get there with human beings.
My name's Patrick and I work on spacecraft systems at the University of Glasgow. So satellites are in orbit around the Earth, but it is possible that they could lose altitude and fall closer towards the Earth. If that happened, they would enter the Earth's atmosphere, and so long as they're small enough, the fact that they enter the air at really high speed generates a lot of heat, and that causes them to burn up. So it's only larger satellites that can really survive and land on the surface of the planet. If a satellite was to break up whenever it's in orbit, that's potentially quite a serious thing, because you've got lots of pieces of the satellite all travelling around at huge speeds and no one really knows where they are. So if they were to collide with another satellite or another spacecraft, they could actually cause quite a bit of damage. So it's important to make sure that satellites don't break up very easily. If a satellite failed to launch, if a launch vehicle failed to fire, then we'd probably have a bit of a problem reorganising the mission and trying to find another slot to try again another day. There's probably about 1,000 satellites operational in space at the moment, but there's perhaps tens of thousands of old ones or pieces of old ones that have stopped working. And these objects are called space debris, and they're all travelling around at huge speeds, so they actually make low Earth orbit a place where you need to be a bit careful. You have to watch out for bits of older satellites as well. So probably the biggest satellite to have come from Scotland is UCube-1, which was a CubeSat spacecraft that was built in Glasgow. It's probably about this size, but of course there's lots of components from that have been made in Scotland would have been integrated into other satellites, and some of them may well have been a lot bigger. A planet has rings whenever its gravitational field is so strong that an object that's close to the planet actually gets stretched apart by the gravity and pulled into pieces. Now, because Mars is quite a small planet, its gravitational field isn't particularly strong at orbital altitudes, and that means it's pretty difficult for Mars to tear things apart and develop a ring of its own. If you want to send a satellite into orbit, you need a lot of fuel in order to accelerate it up to the velocity that you need to maintain orbit. That might be something up to almost 10 kilometers per second. So this is a huge velocity that we need, and that means we need to expend a lot of fuel to get there. And if you look at launch vehicles, you'll see that they're really, really large structures, and a large percentage of that launch vehicle is fuel, perhaps 90 or more percent, is the fuel that'll be used to send just a tiny little bit of the top, the satellite payload, into space. So if we want to send a satellite into orbit, we have to work out how much fuel we need to accelerate it to orbital velocity. That'll be the first part. The second part is we have to work out how much fuel we need to lift it to the height of the orbit. And thirdly, we'll have to work out how much fuel we need to overcome atmospheric drag on the way up. Rockets are always very narrow and pointy, so that they can punch up through the atmosphere very easily. So you can see the effects of some of these drivers in the shapes of the vehicles just by looking at them. People with all kinds of qualifications work in space. Some are engineers like myself who are interested in building spacecraft, but then there are other people, perhaps lawyers, who are interested in what happens when satellites crash into one another, or there could be doctors who are interested in how to keep astronauts healthy whenever they're working in the International Space Station. There are biologists who are interested in whether it be possible for life to form on other planets. So there's lots of people with lots of different backgrounds work in space. I met Buzz Aldrin once, that was quite cool. Whenever different materials are in space, we have the problem that some parts of them get really quite hot and other parts get cold. Here on the Earth, everything tends to stay at a fairly even temperature because the air moves around and transports heat from the hot side of objects facing the sun to the cold side. But that behaviour can't really happen in space where there's no air, and so the problem is sometimes things get really hot, but also sometimes things get really cold, and it's cycling things from going hot to cold that really causes a lot of the damage. Gold is something that's quite shiny, so it's going to reflect away quite a lot of sunlight, but it's not just the heat you have to think of, it's also the cold. You would have to choose the altitude of your satellite according to what you wanted it to do. So if you wanted to have a really good look at the surface of the Earth, you might want to have a satellite that was orbiting quite close, maybe 300 or 400 kilometers up. On the other hand, if you wanted to have a satellite that provided communications over a whole side of the planet, you have to be so far up that you can see the whole of the planet, and that means you would have to be working in a much higher orbit. So it really depends on what you want to do with your spacecraft.
Hi, my name is Dr. Hina Khan and I work as the Innovation Lead for the Scottish Centre of Excellence in Satellite Applications at the University of Strathclyde. So the planets and the rings formed right at the beginning of the solar system, and what happened was, as the solar system formed, there was lots of gas and rocks which were rotating around, which eventually clumped together to form the planets. Now, some of that material, as it was further and further away from the sun, didn't clump into the planets, but actually got caught up within the gravitational pull of as the planets were forming, and some of those elements got trapped within the outer planets. Now, the reason the outer planets, Saturn, Jupiter, Neptune and Uranus, have rings as opposed to some of the inner planets is because they're much further away from the sun, and that means that the gases were not able to actually melt and form part of what ended up to be the gases that filled those planets. So it's almost like it's ice and dust which solidified and then got caught into the gravity of those planets and then essentially got trapped within those systems. Well, that's an interesting thing, and it's something that a lot of people, both scientists and others, have really strongly considered. And the reason for that is it's as research has been going on into the formation of the planets and how each of them became into the state they are today, Mars is very similar in composition to where Earth might have been a number of years, where Mars might have been a number of years previously, so billions of years ago. It is possible that Mars was very similar to Earth, which is why there's always a suggestion that there is liquid water on Mars, or at least there was at some point in time, and that has been confirmed through some of the rovers that we've had. So because of that, there is the potential that if we were looking to migrate to another planet, then firstly because Mars is the closest one to us in terms of being able to get to it, and also it is a safer environment, albeit with additional resources, to be able to create a habitation on Mars. So you know, there is talk a lot about being able to get to Mars and be able to develop systems that would allow us to live on Mars. And that is definitely something that could potentially happen. Well, now that all depends on what you deem as, what you term as exploding. Now, the sun is a star. As we see in the night sky, there are billions of stars out there, and it isn't anything extraordinary in terms of as a star. It just happens to be our star. Now, stars form in different shapes and sizes, and they have different masses, which categorises them in different ways along the kind of the main sequence of stars as they form. Now, like I say, our star is nothing special, so what happens as the star progresses in its life actually depends on the mass of the star, so how heavy it is and what the material is within it. Our star is about halfway through its life cycle at the moment, and because it is of a certain size, it will go down a particular path as it evolves. That path, for in our case, is that it will expand as the hydrogen depletes within the system, within the core of the sun. As that depletion takes place, the sun will expand and become what is known as a red giant. That actually means that it's a larger star, but actually much cooler than it is today. So as it expands, it will grow, and for life on Earth, it will be the end of that, because it will expand to probably encompass up to about the orbit of Mars. Once the expansion has taken place and the core has depleted sufficiently, it will collapse in on itself, because there'll be nothing left for it to hold the reactions together, the nuclear reactions that are taking place. It will collapse into itself, and it will turn into a white dwarf. And that's a fairly typical scenario for a kind of main sequence star. If our star had been more massive, much bigger than it is today in its initial size, then it would form into what would be a supernova. In other words, it becomes so massive that it actually completely explodes in on itself and creates a supernova. That is not the history that the path that our star will go down, and it will just turn into a red giant and then into a white dwarf in about 8 billion years. So nothing to worry about today. So that's an interesting question, actually. And the way to think about it is a satellite is no different than a computer. Your phone or any other technology or a device that you have that can take pictures or images or have information on it. So a satellite is made up of a number of different components, and you may remember from your series what you had as the main parts of what a satellite is. And one of those parts is an onboard computer. Now that computer is there to support the workings of the satellite in order to make things that's moving in the right direction, but also to hold on to that information. And the amount of information that the satellite can hold will depend on the size of the satellite. So the larger satellites, Hubble Space Telescope and some of the Earth observation satellites, which are taking large images of the Earth, will have a much bigger computer on it. Some of the smaller satellites, when you get to the CubeSats and the nanosatellites, will have very small, both in size computers, but also in the amount of memory it can hold. But it's not just about how much information the satellite can hold and where it holds it. It's actually being able to get that information off the satellite and down to Earth. And that all takes power. So you have to do a trade-off between the amount of images or the amount of data that you can hold on your satellite and being able to use power to do that, but also having power in order to transmit it down. So you've got to balance up the amount of information you can have and being able to trade that off with the power requirements. We all have trouble with satellites in space, just like any computer system or technology that you're trying to develop. The key difference here is that once a satellite goes wrong in space, almost nothing you can do about it. So we go through an awful lot of checks and balances to make sure that we can preempt any situation that will occur in space and then have a backup plan to do that. But invariably, yes, things do go wrong, power failures, the solar panels don't deploy properly, which means we can't get the power to the batteries. You can't get power to batteries, you can't turn the satellite on. there can be more catastrophic errors in terms of the computer system fails, or it overheats, or it cools down too much, it freezes, and we've got to really regulate some of these things. But yes, inevitably things do go wrong, and our job as scientists and engineers is to try and make sure that when we're on the ground and we're testing our satellite, that we go through any of those scenarios before launch, because once it's gone, that's it. It's pretty much it's gone. So again, that also happens. So you can do all your testing, everything works well, but then there may be that something doesn't turn on properly, and you've powered your batteries and your computer system has been activated, but then either it doesn't cycle properly, it doesn't power cycle, and you have to restart it, and just the information just doesn't get either taken or we don't get that information down. And these things do happen, and that's a scenario that we need to think about. And it's kind of what has prompted us to look at more reusable or smaller satellite technology. Traditionally, it's been that it would take between 15 and 20 years for a large satellite to go from development phase to launch, and the technology that is there to take that. And it takes a long time, and not only that, but it costs an awful lot of money. So if something were to go wrong, you've lost both a lot of time and a lot of money. Now what's happening is that because of the way technology has gone, both in mobile phone technology and the miniaturization of a lot of these components, means we can start to look at smaller satellites. With smaller satellites, you can build them very quickly, you can launch them very quickly, and you can launch more of them, which means that you almost have a better chance of one of them working or some of them working. And that means, but then even if it doesn't work, you're not that far away from being able to change it, fix it on the ground for the next round, and then launch another one. So that's a process which is becoming more and more commonplace, simply because our technology is advancing so quickly. We want to be able to take advantage of that in space as well as on the ground. There is an argument, and a very solid argument, to have constellations of satellites. Now, constellations of satellite means a large number, anything more than 5 to 10, up to hundreds of satellites. And these tend to be the smaller satellites that we talked about. So there's the smaller satellites which are easily to launch and easier to replenish. But because they're smaller, they hold limited information and have limited power. So that means that they can only be on for a small period of time. But because you have lots of them, you can have them on in sequence. And what that means is that when they're in orbit around the Earth, you can have them in a train, and you can take images almost immediately after one another, which gives you continuous coverage of the whole planet. So whereas one satellite would take, the space station takes an hour or so to go around the planet, you would only get one image every hour, and because you can only take images for a certain amount of time. If you have 100 satellites, then you could have images or data coming down every minute, almost real time. And that's the route that we're trying to get to, that we can have continuous coverage of both images and of data which is coming down. And these things are relevant for security, for being able to monitor our planet effectively, weather prediction, being able to monitor where the weather formations and disasters are taking place and getting that information. So the more satellites, the better. So being a scientist is a career, yes, but it's actually something that people aspire to be. So it's almost like people do it because of the love of the work that they're doing. But in terms of working as a scientist, obviously within the UK, our national working age is 65 odd years in a normal working environment. But the university, particularly in a university environment, you are able to kind of continue your research programs thereafter. I have, known a lot of people who work well into their 70s and their 80s, not because they have to, but because they have that passion that they want to be able to make that difference, and they have a lot of knowledge that they are able to offer the younger generation and provide mentoring to the next kind of cohort of people who are there to take over. So there isn't any age limit, I would say. I think many of us do it for the love of the topic and the subject and the science and the work that we do, and because of that, it's not really deemed as a really not a difficult job, but a job where you're having to, go to under duress and so many. So as far as I'm concerned, I think it's the best job in the world, because in a university you are at the very edge of the best technology and the best research which is taking place. So you're right at the front of where new things are happening and new technologies are being developed, and you have insight into how that can be used in other scenarios and in day-to-day working. So you're the front edge of the new elements of technology which are being taken out into industry and other commercial organisations. So for that reason, you're always doing things new and you're always working in new areas of interest. But equally well, the university is full of very different people. You've got engineers, you've got scientists, you've got computer scientists, you've got geographers, and you've got medics, you've got business people, and it's finding the connection between some of those sectors that allows scientists to really combine some of their ideas. So it's about research which takes into account other people's views, and then thinking of new ways of moving forward that takes advantage of that relevance. So as far as I think, it's a fantastic place to work, and more people should be doing it. So there have been a number of satellite fails, but one is quite personal to me in my career history. When I first started my PhD programme, we get to decide on what the topic is that we're going to be looking at, and I was very interested in looking at the sun and the way the Earth interacts with the sun, and looking at the aurora and the northern lights. And there was a particular space mission which was being launched just prior to my PhD programme called the Cluster mission, which was a European Space Agency led mission, and it was 4 satellites in formation, and they were being launched to be able to provide kind of spatial information about what is happening when the northern lights take place and things like that. And we were all waiting patiently in TV, waiting for the satellite to be launched, and up it went on its Ariane 5 rocket, and after about, a minute and a half, there was a very large fireball in the sky, and what happened was that the shuttle had exploded, carrying all 4 of the satellites, which had taken about 15 years to develop and to put onto this spacecraft. So as I watched my entire PhD program went up in flames, and this is something that we needed to come back from, and there was a lot of discussion as to what we're going to do. But what they were able to do was there was a prototype mission which had been tested previously, and they were actually able to launch that the following year, and things were not as bad as it was. But at the time, when you see your entire life going up in flames, yes, that is a satellite fail.
Hi, my name's Dave Robertson. I work at Glasgow University in the physics department, and I've built little bits of a satellite a few years ago, and I'm here to talk about some of the things that I've done and some of your questions. Satellites are made by lots of different scientists and engineers getting together and building things up. Different satellites require different things. Some require lots of electronics, some require cameras, all of them require computers to control them in some sorts of ways, and they're often built up in big clean rooms with people all dressed up in very fancy kit to stop dust and things getting into them. Lots of different people are involved in building satellites. Obviously there are computers involved in controlling the satellites. You need computing engineers to do that. There are electrical engineers to do all of the electrical systems in the satellite. The whole thing has to hold together, so you need mechanical engineers to make sure that the thing will actually survive the huge shaking it gets going up in the rocket. Different satellites take very different lengths of time to build. Some things like the GPS systems that you use for your navigation systems, all the satellites are essentially identical, so people can build them very quickly in a few months, maybe about a year. Other ones involve very, very different and very strange extra things, and it can take people years and years and years to work out what to build and then to build it up. and test it to make sure that it will actually work. I like this as a question. I think it's a really good question. Satellites sit on top of a rocket, but then if you've ever seen a rocket in a launch pad, you don't see a satellite on top, you just see a solid rocket. And the reason for that is that the rocket goes very, very fast up through the atmosphere. And if the satellite was sitting out there in that huge, huge wind, it would be torn to pieces. So there's a cover on top of the rocket to protect it from the wind. But once the rocket gets high enough up, that cover's thrown off and the rocket still accelerates further. So yes, the satellite goes up in a rocket, but it also goes up on a rocket. So the furthest away satellite from Earth is called Voyager 1. It was launched in, I think, 1977 by the US out to the far reaches of our solar system, and it's actually now been outside the solar system. And it's now 13,000 million miles away from the Earth. To give you, well, it's impossible to imagine that distance properly, but it actually takes light, the radio waves from the satellite, almost 20 hours to get from the satellite back to Earth. So it's a very, very, very long way away.
Hi, I'm Ryan Timoney. I'm a PhD researcher at the University of Glasgow, and I build drills for Mars. To my knowledge, the latest satellite is a satellite called Hispasat. It's a satellite which was launched by SpaceX just the other day. Satellites really range in price. The cheapest satellite could be a kind of electronics board, basically, at like £50. The most expensive satellite, for example, well, a Martian satellite could cost many billions of pounds. Satellites can be really expensive to build. Normally involve many hundreds of people per satellite, so it can be quite expensive. Again, it depends. Small satellites, it could be a small group of people, maybe 10 people, but larger spacecraft, it could be 2,000, 3,000 people easily. Small satellites can be manufactured very quickly in as little as 6 months. Some larger projects could take 10, 20, 30 years even. It could be a whole career for some people. Satellites on the ground undergo a rigorous testing program. They're put onto vibration tables where we shake them to make sure they don't fall apart on the launch pad. We put them in thermal chambers, so we increase the temperature, decrease the temperature, and make sure nothing breaks on the spacecraft. There's plenty of least successful launches. All too often, spacecraft blow up on the launch pad. The rocket just doesn't really go anywhere, which is a disaster. It can cost many billions of dollars to repair or to replace a spacecraft. The most successful spacecraft, that's a tricky question. I consider some of the most successful sort of satellites to be the ones that are currently orbiting Mars, taking pictures. This is, for me, quite amazing. Personally, I've never been exposed to this sort of situation, but when you're fueling satellites with propellant, which they'll use in orbit to move around, sometimes these propellants are very hazardous. In fact, there's a chemical called hydrazine, which is really, really toxic. And so to avoid basically poisoning yourself, the people who are fueling these spacecraft have to wear these big scape suits, they're called, which are basically sort of isolated suits so you can breathe internally without having to inhale any of these dangerous fumes. The biggest satellite I've ever designed was an Earth observation satellite, so a satellite that takes pictures of the ground. It was probably about 600 kilograms and about 2 stories high, and I literally helped from the design on the computer to actually assembling the spacecraft in the facility.
I'm Dr. David Firstbrook. I work at the University of Glasgow, and I develop drilling systems for planetary exploration. Well, unfortunately I haven't actually been in space. Only a lucky few people get that opportunity. However, I'm told that it's very similar when you jump off a trampoline. As soon as you lift off the surface, you're in free fall. So if you take that feeling and just think about what it'd be like to have it for days, for weeks, then that's what it'd be like to be in space. I test things in the lab every day, actually. It depends what kind of day it is. Sometimes I'm analysing the results. Sometimes I'm in the lab here, working on experiments. So the asteroid belt is the area in the solar system with the largest concentration of asteroids. However, unfortunately, it's not like what it looks to be on Star Wars or films. In fact, the average distance between objects in the asteroid belt is actually twice the distance from Earth to the Moon. So it's relatively easy for us to fly our satellites through the asteroid belt. I love working as a scientist. As a kid, I used to play in my sandpit all day, and I decided then and there that I wanted to try and turn this into a career. So I work in my own sandpit here at the university. Well, the biggest satellite around Earth is actually our moon. It's a natural satellite, and we've had it for millions of years. However, the biggest man-made satellite would be the International Space Station.
Hello, I'm Dr. Kevin Worrell. I'm a researcher at the University of Glasgow. I'm currently looking at robotics for drilling and Martian drills. There's not a lot we can do if a satellite breaks. The idea is satellites have been tested so rigorously on the ground that they shouldn't break. However, when they do break, there is very limited options we can do. Normally they've got redundant systems, so if one system breaks, another system will take over. However, in the past, when we used to have the NASA space shuttles, they used to be able to go up and repair the big telescopes, such as the Hubble telescope. Can anything be grown on Mars? Not at the moment, not that I'm aware of at the moment. Maybe as we start to colonise Mars and we start to bring soil and water and hydroponics, then we should be able to start growing on Mars. The equipment can be varied, it depends on the types of system. Anything electronics, you'll need power supplies, radio transmitters, radio receivers, ground stations. You need scales to measure the mass of it. You need metal work to be able to build all the framework. You need electronics workshops. Basically, almost any bit of equipment you can imagine will be used in the production of a satellite. The making of a satellite normally involves the testing of a satellite as well, and from an equipment point of view it would be the test chambers. Before you launch the satellites, you want to be able to test it, so you normally put it into a thermal vacuum chamber. And the thermal vacuum chambers are massive chambers. One in ESA can be about 15 metres in height, and they suck out all the air to generate a vacuum. Then they're able to cool it all down using liquid nitrogen. So all that process can take months and it costs a lot of money. I've personally worked on a number of subsystems that are currently operating in space. One satellite that I worked on, one complete satellite I worked on was the UCube-1 system, where I was responsible for a number of the subsystems, but mainly the altitude control system for it. To date, the smallest satellite I've worked on is a pocket cube. Pocket cube is 5 cm by 5 cm. The one I worked on was 10 cm in length, and that's the smallest satellite that I've worked on to date. It's a difficult question because satellites that are made in Scotland might not necessarily belong to Scotland. However, Scotland at this moment in time are making more satellites per month than any other European country. Also, what you'll find is a lot of Scottish companies make components that are then used in a lot of satellites throughout the world. So actually, we've got a lot of things made in Scotland that are going into space. At this moment in time, putting aside the International Space Station, the most powerful satellite would be EnviSat. It's an environmental satellite. It looks down at the Earth and it collects data about for using remote sensing, and it's looking at environmental issues. It has 6,500 watts. This is the equivalent of 3 kettles, 3 2,000 watt kettles. Spacecraft are really efficient and they use their energy really well, so you can power a full satellite using 3 kettles. There is a number of satellites getting made all across the world. One of the biggest at this moment that's getting made is the James Webb. It's a telescope that will go into space. It's a massive satellite and it's designed to look further into space than any other satellite at this moment in time. So they're normally put on a rocket and launched from the rocket. Also, sometimes they're launched from the International Space Station as well. On board the International Space Station, you've got an airlock, and what they do is they take the satellite to the airlock, put it in the airlock and push it out sometimes. They've also got a pod at the side where they can put a satellite in, and they fire, the door opens and a spring pushes the satellite out. For big satellites on rockets, they normally have explosive bolts. The bolts explode and there's wee springs that push the satellite into orbit.
And that's it. It's the end of Get Me Into Orbit. If you enjoyed this project, we'll be sharing some of the resources and these videos on the Glasgow Science Festival website. Just visit glasgowsciencefestival.org.uk. We'd like to thank the UK Space Agency for funding this project, and we'd like to thank you for taking part. Goodbye, and see you in the future.